Now that we have written the code for the two-pointer search, for the pair sum problem, let's think about the complexity. Let's think of the worst case complexity. Basically, the idea is that we keep searching and we find that none of the pairs added up to the target, right? That's the worst case scenario. But the important point is, unlike earlier, we are now creating only n comparisons because we are now avoiding redundant comparisons. When we know that, adding two numbers is only going to make things, let's say, go away from the target, we are not going in the direction. So the complexity increases as n. In fact, that's what we expect. We'll see this in action later and not at n square. And like we see, this is a significant improvement. Let's convince ourselves of this by logging the runtime. So I come back here to my code. In fact, we'll use the same infrastructure as earlier. So let's just start with, let's say, 1,000 items here. This time around, however, I will call a pair sum efficient. So notice I'm creating a list here, all of positive numbers. I'm logging the time, and here I'm saying, okay, look, find a target which is -100. No two numbers can add up to -100 in these lists. Hence, we are looking at the worst case complexity. But let's see this in action now. So if I were to run this for 1,000, it's 0.001. It's actually faster, quite fast. Let's make it 10,000. The important point, again, notice, is not the absolute numbers, but the way the number scales, right? So I go 10 times more. You notice it has in fact become 10 times. So 3 decimal places earlier, now there's 2 decimal places. I go one more, so that is 100,000, and you realize that this is 0.01. Now, previously, this was something like, a few seconds, in fact, right? Because n square, right? Important point, like I said, is the way this is scaling. I can go one more round, and this will be 0.11. So you can clearly see that, this algorithm is much more efficient because it's taking lot lesser time, number one, and it's scaling as n, and we have come down from complexity of quadratic n square to n, and hence our two-pointer algorithm has really helped us from that perspective. And the efficiency has been increased without compromising the correctness. Here are the results that I got previously when I ran this. Once again, very similar to what we just saw. The important point I'm making is I increase the input size by 10. My running time increases also by a factor of 10, right? So exactly same as earlier. So this is really no surprise. Remember, when we went from linear search to jump search, that is n to square root n, we saw there was a big improvement. Similarly, from the naive method to search for prime numbers, when we went to a smarter method, we searched only into square root n, we saw an improvement. Here something similar is going on. We are going from a naive two pairs, let's say, naive pair sum algorithm to a two-pointer search. We are going from n square to n, and that's exactly what we are seeing here, right? So in summary, we now have a significantly more efficient algorithm, which is to find this pair sum. This works on a sorted list, and this is the two-pointer technique. We'll see more examples of the two-pointer technique in the subsequent videos, but I hope you found this interesting. Do look at our website, www.ybyte.in. We have a lot of such material, and forever enjoy coding. Take care. Thank you so much. Bye-bye.